All right, I want to introduce you to matrices. So a matrix is just a rectangular grid of numbers. And it turns out they're a really convenient way to capture the heart of a linear system, among other things. We're going to spend most of the semester studying matrices, something to do with matrices. That's really one of the main tools of linear algebra. But we're going to begin here. So what I want to do is look at this system. Let's look at the first equation together. And notice the coefficients. The coefficients are 1 minus 2, 1. There's really a 0x1, 2x2 minus 8, so on and so forth. And so the coefficient matrix associated to this system is the following matrix. It's 1 coming from this unwritten 1, and then minus 2, and then 1. Next, we have a 0 coming from the 0x1, then a 2x2 and a minus 8, then a minus 4, 5, and 9. That's the coefficient matrix, and it captures all the relevant coefficients, all the coefficients for the system. It doesn't capture the entire system, and for the entire system, we're going to want to use the augmented matrix. And so the augmented matrix is the same thing as the coefficient augmented matrix. It's the same matrix as the coefficient matrix, you just add a column. So you take the coefficients, so 1 minus 2, 1, but then you go ahead and make another column with the constants. So then a 0, 0, 2, minus 8 is equal to 8, and then minus 4, 5, 9 is equal to minus 9. And if you have eyes to see it, given an augmented matrix, you can quite literally write down the linear system and vice versa. It's the same information. And there's a lot of benefits to this notation computationally, but the main thing is that it's just cleaner and easier to work with. I don't need to write down x1, x2, and x3. Simply where I put the numbers tells me. I can read off that this equation says 0x1, 2x2 minus 8x3, 2x2 minus 8x3 equals 8. It's always equals the last number. Okay, so a couple of things. We're going to talk about the size of a matrix, the size or dimension of a matrix. And it's always given row by column. You're going to want to memorize that like right now. Row by column, row by column, row by column. Okay, so the coefficient matrix has dimension. Well, there are 3 rows. You can count them 1, 2, 3, and 3 columns 1, 2, 3. So it's 3 by 3. That's how we write it. Okay, and the augmented matrix. Yeah, I thought something looked funny. I think I got an extra little, I got an extra little E in there. Something didn't feel right and I wasn't paying attention. We'll just fix that. Augmented matrix. There we go. The augmented matrix has dimension while I'm writing. See if you can count it. Has dimension. Well, okay, row by column. So 1, 2, 3 rows, 1, 2, 3, 4 columns. So this would be a 3 by 4. And let's just go ahead and note that in general, an M by N matrix has, it's row by column, so it has M rows and N columns. All right, very good. So that is a convenient way for us to write down a linear system in matrix form. We're typically going to focus on the augmented matrix. We're not going to look at just coefficient matrices so much because it's leaving off a very key part of the system, but I want you to know what the coefficient matrix is. Okay, so think back to how you would solve equations, maybe an equation like this. If I gave you 3x1 plus 2x2 equals 2, and then I said something like, I don't know, 6x1 minus 2x2 equals 12. you might look at this equation and you might say, hey, I can eliminate the variable x2 by adding this equation to that equation, and or maybe there would only be just a minus x2 there, and you might say, well, I'm going to multiply the top equation by 2 and then add that to this equation, and I would get something like 12x1. Oh, I'm sorry, no, not top equation by 2. I'm going to multiply the bottom equation by 2 and then add, well, my eraser is so small it's not working. Multiply the bottom equation by 2 and then add to the top. And so you would say, well, 2 times 6 is 12, plus 3 is 15x1, 2 times minus 1 is minus 2, plus 2 is 0x2, and then 24 and 2 is equal to 26. And the point is, at this point, you can solve. You could solve for x1 and then go back and solve x2. So you can obviously switch rows easy enough. It doesn't change the system at all if you decide that you want to write this equation first or second, right? That doesn't change anything. So you're obviously allowed to change the order of the equations. We know from just experience working with these equations that at least for 2x2 systems, you can multiply an equation by a number. That doesn't change it. Non-zero number. So I can multiply this one by like 2 and replace this this equation with what I get when I multiply by 2. And you can actually replace an equation by multiplying and then adding. And each of those gives you an equivalent linear system. And so that brings us to the following. So these are called elementary row operations. And given a system of linear equations,